Hello friends, welcome to our channel. In previous videos, we discussed about clause sets and limit points of a set and derived set of a metric space. In today's video, we will discuss closure of a set in a metric space with some results based on closure of the sets. Theorem. Let A be any subset of a metric space XD, then A closure is closed set. Proof. Let XD be any metric space and capital A be the subset of X. We have to prove that A closure is closed it is sufficient to prove that A closure its complement is open, that is X minus A closure is open. We know that A closure is equal to A union D of A, where D of A is the derived set of A. That means the collection of all limit points of A. Suppose X is belongs to X minus A closure. This implies X does not belongs to A closure. This implies X does not belongs to A union D of A. This implies X does not belongs to A and X does not belongs to D of A. This implies X does not belongs to A and X is not a limit point of capital A. This implies X is not an adherent point of capital A. So there exists R greater than 0 such that sphere centered on X with radius R intersect with A is equal to phi. Now we have to prove that SRX is contained in X minus A closure. Let Y is belongs to SRX be arbitrary. We know that every open sphere in a metric space is always open set. Therefore, SRX is open set. This implies SRX is neighborhood of all its points. Therefore, SRX is neighborhood of Y. So, there exists R1 greater than 0 such that sphere centered on Y with radius R1 is contained in SRX. This implies sphere centered at Y with radius R1 intersect with A is contained in sphere centered at X with intersect A. This implies sphere centered at Y with radius R1 intersect with A is equal to phi, because SRX intersect with A is equal to phi. This implies Y is an adherent point of capital A, that is Y does not belongs to A and Y does not belongs to D of A. This implies Y does not belongs to A union D of A, which is equal to A closure. This implies Y does not belongs to A closure, so Y is belongs to X minus A closure. But Y is an arbitrary point of SRX. So, SRX sphere centered on X with radius R is contained in X minus A closure. This implies X is belongs to SRX contained in X minus A closure. Therefore, X minus A closure is neighborhood of X, but X is arbitrary point of X minus A closure. Therefore, X minus A closure is neighborhood of all its points. Thus, X minus A closure is open set. This implies A closure is closed set. Next theorem. a subset A of a metric space XD is closed if and only if A closure is equal to A. Proof: let XD be any metric space and A be the subset of X. We assume that A is closed subset of capital X. We have to prove that A closure is equal to A. We know that A closure is equal to A union D of A is equal to A because D of A is contained in A as A is closed. So, A closure is equal to A if A is closed. Conversely, suppose A closure is equal to A, we have to prove that A is closed, that is A contains all its limit points A closure is equal to A. This implies A union D of A is equal to A. This implies D of A is contained in A, that is A contains all limit points of A. This implies A is closed. Hence, A is closed if and only if A closure is equal to A. Next theorem, let XD be any metric space and A, B are subsets of capital X such that A contained in B, then A closure is also contained in B closure. it is given that XD be a metric space, A and B are any two subsets of X, A is a subset of B. We prove the closure of A is also a subset of closure of B. Let XD be any metric space and A, B are subsets of capital X such that A is contained in B. Let X is belongs to A closure. This implies X is belongs to A union D of A. That is, either X is belongs to A or X is belongs to D of A. This implies X is an adjoint point of A if X is belongs to A, then sphere centered at X with radius R intersect with A does not equal to phi for every R is greater than 0. If X is belongs to D of A, that is X is limit point of A, so there exists sphere centered at X with radius R intersect with A minus X does not equal to phi. This implies sphere centered at X intersect with A does not equal to phi. So, in both cases, either X belongs to A or X belongs to D of A, we have sphere centered at X with radius R intersect with A does not equal to phi. Put it equation number 1. Now, sphere centered at X with radius R intersect with A is contained in sphere centered at X intersect with B, because A is contained in B. This implies SRX intersect with B does not equal to phi, because by equation 1, as SRX intersect A does not equal to phi, therefore their superset is also not equal to phi. This implies X is an adjoint point of B, that is, either X is belongs to B or X is belongs to D of B. This implies X is belongs to B union D of B, which is equal to B closure. But X is arbitrary point of A closure. Thus, A closure is contained in B closure. So, if A is a subset of B, then A closure is also a subset of B closure in any metric space XD. Next theorem. XD be any metric space and A, B are subsets of X, then A intersection B closure is contained in A closure intersection B closure, and A union B closure is equal to A closure union B closure. Proof. Let XD be any metric space and A, B are subsets of capital X. We know that A intersection B is contained in A and A intersection B is contained in B. A intersection B contained in B. This implies A intersection B, its closure is contained in A closure, and A intersection B closure is contained in B closure. As A contained in B, then A closure is contained in B closure. This implies A intersection B closure is contained in A closure intersection B closure. Again, A is contained in A union B and B is contained in A union B. This implies A closure is contained in A union B closure and B closure is contained in A union B closure. This implies A closure union B closure is contained in A union B closure. Put it equation number 1. Now we have to prove that A union B closure is contained in A closure union B closure. Let Y is belongs to A union B closure. This implies Y is an adjoint point of A union B, that is, sphere centered on Y with radius R intersect with A union B does not equal to phi. This implies either sphere centered at Y intersect with A does not equal to phi, or sphere centered at y with radius r intersect with B does not equal to phi. This implies either y is an adherent point of A, or y is an adherent point of B. This implies either y is belongs to A closure, or y is belongs to B closure. This implies y is belongs to A closure union B closure, but y is an arbitrary point of A union B closure. This implies A union B closure is contained in A closure union B closure. Put it equation number 2. From equation 1 and 2, we have A union B closure is equal to A closure union B closure, where A and B are any two subsets of a metric space XD. Next theorem. Let XD be any metric space and A be the subset of capital X, then prove that A closure is the smallest closed set containing A. Proof. Let XD be a metric space and A be any subset of capital X. In previous theorems, we already proved that A closure is closed subset of capital X. Now we have to prove that A closure is smallest subset of X containing A. Let it possible we assume that B be any closed subset of X containing A, that is B is closed and A contained in B. As A contained in B, this implies A closure is contained in B closure, which is equal to B, because B is closed. So B closure is equal to B. Thus A closure is contained in B. So A closure is the smallest subset of X containing A. Next theorem. Show that for any metric space XD, A closure is the intersection of all clause sets containing A. Proof. Let XD be any metric space and A be the subset of X. Suppose F1, F2, F3 and so on are the closed subsets of capital X containing A. We have to prove that A closure is equal to intersection F lambda, lambda belongs to indexing set, that is F1 intersection F2 intersection F3 intersection so on. Let F is equal to intersection F lambda, lambda belongs to indexing set. As F1, F2, F3 and so on all are closed sets containing A. This implies A is contained in intersection F lambda, lambda belongs to indexing set which is equal to F. Thus, F is a closed set containing A, but we know that A closure is the smallest subset of capital X containing A. Therefore, A closure is contained in F. Put it equation number 1. Now we have to prove that F is contained in A closure. Let X is belongs to F, then X is belongs to F lambda. For every lambda belongs to indexing set. This implies X is the element of each subset of X containing A, but A closure is also a closed set containing A. This implies X is belongs to A closure, but X is an arbitrary point of F. So, F is contained in A closure. Put it equation number 2. From equations 1 and 2, we have A closure is equal to F is equal to intersection F lambda, lambda belongs to indexing set. That is, A closure is the intersection of all closed subsets of a metric space containing A. It is sufficient for today's. In the next video, we will discuss subspace of a metric space and some results based on subspace. So keep in touch, watch our videos and subscribe our channel for more videos on these topics. Thanks to all. Have a nice day. Bye bye.